Hello everyone, this is Physics 2 for the fall of 2017 project. So what topics we're going to cover today are going to be over properties of charge using Coulomb's law, and then we're going to do an example problem over these topics. So the question is, what is a charge? A charge, there's two types. There's positive and then there's negative. If the charges are alike, they're going to repel. And if the charges are unalike, they're going to attract each other. Charge is conserved and also quantized.
Our example problem today will be revolved around Coulomb's law and the notion that like charges repel and unlike charges attract. We will be evaluating as well the net electrostatic force, which is K Q1 Q2 over R squared, K being Coulomb's constant, 8.99 times 10 to the 9th newton squared per Coulomb squared. Q1 and Q2 will be our respective charges, and R being our distance between the two. In this case, we'll be evaluating charge 3. Our results will show that, again, like charges repel and unlike charges attract.
Hello, people and peopleettes. So where do we leave off?
Point charge?
Yeah.
Something about point charge? Okay.
Yeah.
What's the formula for a point charge?
Uh,
Oh, over there in the back. I heard it. Okay. Where's my deleter?
I got you.
The formula for a point charge, the electric field for a point charge is E equals KQ over R squared. Now, as you will see up here, it says Coulomb's law. Does anybody know what that formula is?
F times Q. No,
Q1.
that's really wrong.
Coulomb's law. The force electrostatic is equal to K charge 1 charge 2 over R squared. Does anybody know what the R stands for?
Distance.
The distance. Yes, it's the it's the distance. Okay, so now we're going to take a look at an example problem called 3 charges in a line. Okay, so let me see what it how they set it up in the book. This is charge 1. Charge 2 is equal to positive 2 microcoulombs, and charge 3 is equal to negative 6 microcoulombs.
Go.
So now that we've rewritten the problem, can anybody tell me what the formula would be to use for this?
K Q1.
Coulomb's law.
Coulomb's law.
Coulomb's law.
Yeah.
Okay.
Right. My bad.
So, so the net force is going to be equal to the force charge 3 due to charge 1 plus 3 due to 2. Correct?
Yeah.
So now you said Coulomb's law. What is Coulomb's law?
F equals K Q1.
Okay.
Oh, Q3. My bad.
Here's Q3.
Q1.
Q1 over R squared. What does the R stand for again?
Distance.
The R is the distance between these. Okay. So for the first one, we're going to use, what is K? What is the K value?
8.99 times 10 to the 9th.
Newton meter squared per Coulomb squared.
Right.
Yeah, do that or you're not getting any partial credit. Okay. So charge 3 is negative 6 microcoulombs. But since we're just getting the magnitude, we're not actually going to use that negative charge right now. So 6 times 10 to the negative 6 coulombs times, we're going to go down here, charge 1. It's another negative one, but we're just going to do it as positive. 10 times 10 to the negative 6 coulomb. Now, can somebody evaluate that for me?
Did you do R squared?
Of course
R
not.
squared?
Thank you. You're going to pass. Now, what's the distance between charge 3 and charge 1?
0.25 meters.
Okay. force of charge 3 due to charge 1 is, does anybody have an answer? I'm gonna use the book. I'm gonna use the book calculator. Okay, so, all right, I got 8.63 newtons. Okay, now for the second one, we're gonna do the exact same thing. So 3 due to 2 is equal to 8.99 times 10 to the 9 Newton meters squared per coulomb squared. Charge 3 is equal 6 times 10 to the negative 6 coulombs. And charge 2, 2 times 10 to the negative 6 coulomb. Over what is the distance between charge 3 and charge 2? 0.15 meters
Squared.
And we're going to use the book calculator again. Silly students. Okay. Equals 4.79 newtons. Okay, now, if we go over here to this formula, we have all of our values for it now. So, the total force electrostatic is equal to force of charge 3 due to charge 1, which is 8.63 newtons, plus 4.79 newtons. But not so fast. We never thought about our, our negative signs. So on the charge 1 and 3, which is this one right here, these things repel. And if we consider this as like a coordinate plane, with this direction, the right is positive x, charge 3 will be moving to the right, so that 8.63 will be positive. Now, considering charges 3 and charge 2, these two will attract. So charge 3 will be going to the left, which will make this a negative. Now, can anybody do this addition for me? Or no?
Okay. I got 3.84 newtons.
Okay, that's what the book calculator says too. Okay. That is the net force. Now, which direction will it go? Since it is positive, it will be going to the right direction. Okay.
Go.
Hello. Our example problem completely supported our hypothesis that like charges repel and that unlike charges attract. If we look here at the force on charge 3 due to charge 1, we get a value of 8.63 newtons, which is a repulsive force going in the positive right direction. These two charges repel, charge 3 moves to the right. If we look at the force on charge 3 due to charge 2, we get 4.7 newtons. But since this is an attractive force and it pushes charge 3 into the negative x direction, we'll assign this a negative value. If we take the sum of these two forces, we're going to get a net electrostatic force of 3.84 newtons, which pushes charge 3 out to the positive x direction.
And this concludes our project for today. We examined the properties of a charge, Coulomb's law, and how we could use Coulomb's law to find net electrostatic force. And these effects two charges have on one charge. Bye.